For the last part of Chapter 11, we'll look at CO2 and global warming, future changes in CO2, other greenhouse gases and their predictions, methane and nitrous oxide specifically, a little bit at thermal pollution, changes in the temperature record, future changes in temperature that coincide with the increases in greenhouse gases, and ultimately the scientific consensus on global warming. So quite a few things to look at here. All right, to get our bearings here, they're stepping through the years, each season of the year. The first thing you see is the northern hemisphere on the right side of this graph is going up and down quite a bit more than the southern hemisphere, and that's simply because of those active fluxes between the huge amount of land mass there, the plants, and the atmosphere. So you can see that breathing of the biology every season in the northern hemisphere. Over here, they're just simply showing the hemispheric averages. More specifically, they're looking at the South Pole in the blue. You can see there's not a whole lot of seasonality there. And then Mauna Loa, which is here in the northern hemisphere, a lot of seasonality because of those plants. Overall, though, this whole graph's getting displaced upwards over time, whereas this graph is clearly ticking upwards on long time scales. Now you do see some large deviations in certain spots in the northern hemisphere. That's most likely to do with either some kind of deforestation, biomass burning, or even city effects. Now the visualization starts to go backwards in time, to go farther in the past and compare to what happens in modern times with what has happened throughout history as measured from ice cores and other methods. So this is looking at an ice core, the Law Dome ice core, seeing that it was fairly stable at 280 parts per million for quite some time in the past there. They're now gone back 2,000 years. And then we're getting into a different ice core. We're starting to get into the Vostok ice core, which, as you know, goes back 400,000 years. You're going to start to see those ice ages that happen in the Pleistocene with regular oscillations of about 100,000 years, where CO2 concentration went from roughly 180 or 200 parts per million and jumped up to 280 and back again with a periodicity of about 100,000 years again. Now we're getting into the Dome sea ice core record, which goes back to 800,000 years. So it's very clear that the CO2 increase right now is very unnatural. We've also seen the modern surface temperature increasing over time since the Industrial Revolution, increasing from 1850 until present by about 1 degree Celsius, which doesn't seem like a lot, but in a global average, that is a lot. And there's certain regions in the globe that have warmed much more, specifically the Arctic regions. Sea surface temperatures have also been on the rise. They've been going up quite a bit, pretty much globally. Now, looking at a first review of greenhouse gases, when we first looked at the energy budget of the Earth, we considered it to be a black body. In other words, we didn't consider an atmosphere. We considered sun's radiation came in, was spread over half the Earth, and then the Earth having a temperature above absolute zero emitted from all sides of the Earth, and it emitted infrared because of the temperature there. So without greenhouse gases, the infrared transmits straight through the atmosphere, and that's what we considered with effective radiation temperature. However, with greenhouse gases, the IR is partially absorbed in the atmosphere, which warms it. Anytime you absorb radiation like that, it's going to warm the layer where it's being absorbed, but also those greenhouse gases will emit plenty of IR radiation back down to the Earth's surface, giving a second heat source to the surface effectively. So now we have the sun's heat coming in, but we also have heat coming in from IR radiation. This visualization is going to look at the greenhouse effect. So right now we don't have greenhouse gases in the visualization. We have visible photons that have higher energy coming in, getting absorbed by the surface, and then IR photons with lower energy being emitted by the surface and escaping to space. There's more IR photons leaving than are visible coming in, but there's still energy balance since the visible ones have more energy associated per photon. So now we can increase the number of photons just to see it a little bit better, and then we can have a little bit of greenhouse gases visualized by a glass pane. So what happens here is the glass pane is a selective absorber, which means that it's not absorbing the visible, just like greenhouse gases, but it does absorb a certain percentage of the IR photons, and it also re-emits or emits IR photons in both directions. The net effect of that is that it helps trap IR photons near the surface. So the more glass panes you get, the more this effect integrates up, and you tend to get more IR photons trapped near the surface, which, as you can see, is increasing the heating over time. So temperature-wise, if you add one pane of glass, it's going to trap in a certain amount of IR radiation. It's going to raise your temperature because that's one form of heat. Having IR being absorbed is going to heat you up. And now you raise another pane of glass, and it's going to heat you up even more because it's more effective at trapping those IR photons near the surface. At the top of the atmosphere, you might still have a general energy balance as far as IR escaping and visible coming in, but at the surface, the IR is spending more time down there, so absorbing it. So this study from Nature in 2011 considered outgoing long-wave radiation from 1970 to 1996, and what they found is at the top of the atmosphere, there's actually less long-wave escaping, and that's because we've loaded the atmosphere with greenhouse gases. The type of wavelengths associated with CO2 are not coming out as much, and that makes sense because we've loaded the atmosphere with CO2. So not as much of that wavelength is escaping in 1996 when compared with 1970, and also methane too. The wavelengths associated with methane, less is escaping in 96 than in 1970. Less long-wave radiation escaping to space. Where did it go? It must be trapped near the surface, raising the global temperature. So the worry here is that temperature changes went with past CO2 changes. This is looking at 800,000 years back from the dome sea ice core, and every time the CO2 concentrations flopped by about 100 parts per million, the temperature changed by about 10 degrees Celsius. Will this happen again? We've already shown in previous lectures that our models can simulate what has happened with atmospheric temperature pretty well in the last 100 years by using both greenhouse gas loading and other natural forcing mechanisms like volcanoes. So the actual observations are the black line here going up and down, but a general trend upwards. And our models, there's a lot of spread between different models shown by the spread of the spaghetti here, the different model runs here. However, the average shown in the dashed blue line pretty well matches this, and it certainly matches the overall trend upwards pretty well. However, if we use those same models and just take out the effects of greenhouse gases, which is why you use models, you can do experiments like that. If you take out the greenhouse effects, we do not get an accurate representation of what the temperature record showed in the last 100 years, which says that we really can't model these things without using greenhouse gases. So I'm not saying that's truth or not, but it's very interesting that the most sophisticated models cannot represent what happened in the last 100 years without using greenhouse gases. And then when they do use greenhouse gases, they represent that change pretty well. The computer models match the observed change in temperature on all continents pretty well. So the red swaths here are the model runs using natural variability and greenhouse gases. The black thick line is the observed temperatures in North America, Europe, Asia, Australia, Africa, South America. If you do not use the greenhouse gases, you get model runs in the blues here that don't match what happened there. So again, that's not specific globally. There wasn't some kind of magic average that made our models work. Our models work with greenhouse gases in all the regions. As the NOAA simulations showed, air bubbles trapped in ice cores in the past show nothing like our CO2 rise in the last, say, million years or so. So this anomalous rise in CO2 is truly anomalous. We haven't seen anything like it in the natural variability for at least 1 million years. So where exactly is all the carbon coming from? Well, first of all, you had the pioneer effect starting in about 1850, where people were cutting down a lot of trees to grow crops, etc. And so that land use change resulted in a lot of carbon emissions during the decomposition process. You're also removing, again, a sink by taking down a lot of trees. After that, we started to use coal. As the rise of coal came about, we started to use oil quite a bit too, and the other fossil fuel gas too. So right now it's pretty well split, although coal is definitely by far the dirtiest fossil fuel. And by that I mean you get the least amount of energy per pound of CO2 emitted by using it. And these are specifics that we'll look at in the future classes. In the ice cores, the air bubbles also show methane and nitrous oxide going up extensively, and we have never seen a rise like that in natural variability for at least 650,000 years. Now, when people think of methane, they generally think of swamps, and that's generally true. The natural sources of methane are wetlands and typically swamps. There can be termites, oceans, and some other parts too. The anthropogenic sources, the sources from man, are pretty well split. Rice cultivation is one, cows, cattle, things like that. Biomass burning, fossil fuels, and then waste decomposition in landfills and such. Methane has a pretty short lifetime compared to CO2. Methane readily reacts with oxygen in the atmosphere, so you usually have to have quite a bit of a source in order to get a reservoir of methane built, because the sink of methane is quite quick. The other thing it can do is float up to the stratosphere, where again it reacts with oxygen, and it makes water vapor up there, which again is a potent greenhouse gas. Methane oxidation is the primary source of water vapor in the stratosphere, actually. So this is where the stratosphere gets most of its water vapor. Other things for methane to think about is as the permafrost melts in the subarctic, which is doing it at an alarming rate right now, methane that's been trapped underneath by the ice can bubble to the surface now. Also, these ponds are now devoid of oxygen. They're kind of stagnant because they don't have an inlet and outlet to replenish the oxygen. This encourages methanogens, which are bacteria that form methane. This can lead to even more methane and lead to global warming and more melt. And so it's a positive feedback effect that could be in play. Here's just a little aside, looking at some of these areas where the permafrost melting, you get these interesting effects of bubbling up of gases. What's happening underneath that pillow of sod is effectively a methane amount of gas that built up that's trapped by the turf there, and they're kind of jumping on it and now releasing the gas out of the ground there. So we're seeing this bubbling up from lakes, we're seeing it bubbling up underneath turf, we're seeing a lot of methane coming up in the subarctic regions. Now, nitrous oxide is another greenhouse gas. There's not a ton of it in the atmosphere today. However, it's on the increase. It's increased about 20% since 1850. There are natural sources of nitrous oxide. The anthropogenic component's about 38% of the total amount of nitrous oxide today. The main source of nitrous oxide from humans is agriculture. So simply said, this is really from adding a lot of fertilizer to fields. That can be a big source of nitrous oxide in the atmosphere. So interestingly, your book, and a lot of books are dated once you use them for a while, forecasts made in the year 2000 place the date of reaching the 400 parts per million level at the year 2025. Well, we're well past that now. Here we're looking at January 2017, where global average CO2 was 405 parts per million. Shown here is emissions from fossil fuels and cement in gigatons of carbon per year. And they're showing the historical emissions over time from 1980 going up to about 2014. And there's predictions made right here at about 2007 by the IPCC reports. And that report had 4 scenarios trying to figure out what humans are going to do in the future, because that's going to be a big player in how the evolution of CO2 concentrations go up. So the scenarios shown are the red line coincide with the representative concentration pathway, 8.5. That means that continued fossil fuel driven economic development until 2100. So basically business as usual. So obviously you're going to use a lot of fossil fuels and drive up CO2 quite a bit with that scenario. RCP6 says no global coordination, but many clean energy alternatives by 2050. That seems pretty likely to me. There's definitely a rise of clean energy alternatives happening right now. Hopefully they keep increasing. So of course that's not going to go up as much as the RCP 8.5. Then you have RCP 4.5. The world imposes limit on fossil fuel usage. In other words, the Paris Agreement comes into play and you even get stronger regulations, and emissions start to fall by 2050. And so that's the yellow line here, showing that emissions would decrease. That doesn't mean overall CO2 concentrations would decrease. That just means the emission rates would decrease. Now you have the RCP 2.6, which was a very optimistic viewpoint. Peak emissions in 2 to 3 years from that 2007 report, and then carbon neutral by 2050. So that would take emissions down relatively quickly, getting you across the boundary here where you have negative emissions, meaning you're scrubbing out more CO2 artificially or by planting more trees or something like that than you're emitting. So a very optimistic scenario. What I'm trying to show here, first of all, is that when these model predictions were made, this was the worst case scenario, was the red line here. That's the worst we could do. And the actual, we did that bad. So our actual track was right along the worst case scenario. And that really hasn't changed a whole lot globally yet. Hopefully it will. So where do those RCP numbers come from, those representative concentration pathways? What does 8.5 mean, for example? The RCP number corresponds to the expected radiative forcing in watts per square meter by 2100 due to the anthropogenic CO2 and its feedbacks. Okay, so they're taking those predictions and saying, okay, the RCP 8.5, if we keep emitting a lot of CO2, that's going to raise temperature, and it's going to raise it specifically by increasing the amount of watts per square meter getting absorbed at the surface. And that's where the 8.5 comes from. So by the year 2100, you can see the blue line lines up with 8.5 watts per square meter. So again, they're just correlating the amount of greenhouse loading to the expected amount of radiating forcing at the surface due to it. And all the other scenarios line up the same way. Now you can look at the total CO2 concentrations from the different scenarios, and you'll find business as usual by the year 2100, the 8.5 scenario will get us to about 950 parts per million of CO2. So quite a bit, more than double what we're at now, which is about 405 parts per million. The other scenarios are somewhere in between. Going to the most optimistic scenario, the 2.6, we actually drive down the concentrations after we reach a peak somewhere around 2050, and then we start to drive them down. Again, the way we drove them down there is because we'd have to have negative emissions, meaning we're scrubbing more CO2 than we're emitting at that point. That's the only way to get them to go down in that short of a time frame. Looking at methane, again, if you do the worst case scenario, fossil fuel burning, you're going to get a lot of methane. The other scenario is not as bad. In fact, the 2.6 scenario, methane will almost immediately start to decrease if we decrease our fossil fuel burning to almost nothing. Nitrous oxide, again, same kind of scenario. They go the same direction. So CO2 is a big player in the future, it seems, although there's plenty of uncertainty about the methane sources from the permafrost. Here's a graph that's often looked at, looking at the total scenarios of anthropogenic forcing at the surface. So we're looking at the top, the long-lived greenhouse gases, CO2, we know that's going to be a positive forcing at the surface. So the amount of radiating forcing at the surface is going to be positive as man increases CO2. There's some error on that, but not a whole lot. Then you have nitrous oxide here as the orange, methane as the red here, halocarbons, which are another form of greenhouse gases. Ozone is another greenhouse gas in the troposphere, so we have increased ozone in the troposphere, and that will add to the radiative forcing in the future at the surface. Stratospheric water vapor from methane. Again, as methane goes up into the stratosphere, it creates water vapor during oxidation, so you end up with more water vapor up there, which will increase your warming at the surface as well. And then we get into surface albedo effects. We've looked a little bit at land use. Overall, there's been a tendency to take down forests and replace with more grasslands, raising the albedo, making the radiative forcing at the surface go down a bit because it's more reflective. You're not absorbing as much at the surface. We haven't looked on black carbon on snow, but you can imagine simply pollution or more wildfires adding black carbon, which might fall on snow, lowering the reflectivity, adding to the radiative forcing by lowering the albedo. We've looked at aerosols in this class a little bit. This is specifically looking at anthropogenic aerosols, so pollution. As you load those up in the atmosphere, the best guess for us is that they will cool by scattering away a lot of sunlight, not letting it reach the surface. So that's going to be a negative radiating forcing. Also the cloud albedo effect, more aerosols, more cloud condensation nuclei, more clouds. That is also going to make it more reflective, less solar at the ground. So we've looked at this before, but this total net anthropogenic radiative forcing is a combination of all these things. And most of it is from CO2 loading. As you can see, this corresponds with the big red bar at the bottom. But however, most of the uncertainty lies with what we know about the aerosols here. We don't have those resolved terribly well. Lastly, we'll look at thermal pollution, waste heat going into water or air. And this is something people should start to think about when they're trying to make innovative ways to conserve energy in the future. So this thermal image of houses in front of a coal-fired power plant shows the loss of energy through heat. We're measuring this with an IR thermometer. It's measuring the heat coming off this. So the point is, at the same time, you're not using that heat to energize yourself or to keep you warm inside the house. You're actually heating the atmosphere by doing this. So if you can actually create a way, more better insulation to keep that heat being used by humans and not wasting it into the atmosphere, it'll do two things. It'll just conserve energy so somebody else can use it. It will also limit the amount of heat that the atmosphere takes on. So an article in the Journal of Geophysical Research, Atmospheres, calculated the anthropogenic heating of the urban environment due to air conditioning. What they found, and they were specifically looking at Phoenix, Arizona, what they found was waste heat from air conditioning usage increased temperatures at about 2 meters up by 1 degree Celsius at night in Phoenix. So more AC was needed because now the nighttime air temperatures were higher. Using the waste heat would be great. In other words, to get the extra heat generated outside by this air conditioner, if you could trap it and heat the water in your home, that would be a better usage of that energy. Another graph from the IPCC report here showing atmospheric CO2 concentration till the year 3000 and surface air temperature change till the year 3000 as well. I'll quote them: "A large fraction of anthropogenic climate change resulting from CO2 emissions is irreversible on a multi-century to millennial timescale, except in the case of a large net removal of CO2 from the atmosphere over a sustained period." So what they're saying is, whatever concentration you get up to, you're somewhat locked to that concentration for a long period of time, thousands of years here. And as such, the correlating air temperature change is also locked in for the most part. So the climate system has plenty of inertia in it, and if you push it too far, it's hard to get it to reverse itself. It's hard to get sinks to take up that much CO2 on smaller timescales. Here's looking at the temperature change relative to the 1986-2005 average. We're going all the way to the year 2100 here, just looking at the spread or the standard deviation of the data here. Here's the orange looking at internal variability. So this is natural variability in the system, how much it might change things in the future. Not a whole lot. Model spread is shown in blue. Yes, the models do represent physics a little bit differently between different models. So they definitely have some spread in here as well. Here's the RCP scenario spread. Okay, so the most spread here is due to our choices essentially. Which scenario are we going to follow? The business as usual, the 2.6 was a very optimistic future, or somewhere in between. I just show this to indicate that a lot of the variability in future climate states relies on our decision. A global increase in temperature will be accompanied by shifts in the equator to pole temperature gradient. The poles are warming 3 times faster than the tropics. This changes the atmospheric circulation and the weather patterns. Most of the science says this will lead to a widening tropical belt. So the subtropical zone is expected to expand poleward, making those areas that are already dry in the subtropics even drier, and then areas just poleward of them also dry. The jet and associated storms move poleward. So again, if the temperature gradient moves poleward, the jet forms right above that temperature gradient, so it's going to move up there, and the associated storms that the jet spins up will move up there as well. So they expect the storm track to move slightly poleward. The Arctic vortex specifically is in the northern hemisphere, and it's expected to contract poleward, meaning that this big area of kind of cold air that extends pretty far into the mid-latitudes now is going to push and hang out most of the time to the far north. So you've probably heard the news that many organizations voice that limiting global warming to 2 degrees Celsius or less could help avoid the most severe impacts. Even some other studies said 1.5 degrees Celsius would be the number we want to keep to. Only RCP 2.6, with peak emissions in 2 to 3 years, carbon neutral by 2050, gets us below that 2-degree mark. What it realistically takes is to be carbon neutral, equal removal and emissions by 2050. So here we are at the zero emissions here, neutral emissions here, and carbon negative, more removal than emissions thereafter. So all these lines here are falling below zero, meaning more removal than emissions. That's what it's going to take, and here's the temperature increase relative to pre-industrial times shown on the right here, that by 2050 we kind of turn it around by starting to scrub out some of the CO2, removing it from the atmosphere. That helps stabilize us below that dangerous 2-degree mark. So again, 97% of climate scientists agree that humans are causing global warming. This has been shown in a number of reports, and if you want more information, you can look at this link at Skeptical Science. The public, however, have a very different viewpoint. The question for this survey was, what percent of climate scientists agree that humans are causing global warming? With liberals generally saying that 60% of climate scientists agree humans are causing global warming. And then conservatives, definitely, it depended how conservative you are. However, in general, they thought about 40% of climate scientists agree that humans are causing global warming. So just kind of an interesting statistic to think about. Nobody's even close to understanding that 97% of climate scientists do agree on this fact, or at least they don't want to believe that. Key points from this final lecture on Chapter 11. Long-lived greenhouse gases, for example CO2, methane, and nitrous oxide, have increased significantly, very significantly, since pre-industrial times. The rate of future increase will largely depend on political decisions and technology as well. Our models predict warming increases with greenhouse gas increases, and 97% of climate scientists trust this. Due to the inertia of the system and the emissions thus far, we are already locked into some future warming already. To keep this warming below 2 degrees Celsius, we must act fast and be carbon neutral by about the year 2050, and then carbon negative thereafter.